Hi everyone, thanks for coming. I'm going to talk about the limits of multitask peer prediction. This is a joint work with Fang-Yi and Yiling Chen. So let me start with some background about peer prediction. Peer prediction refers to the problem of eliciting truthful responses from people when their reports cannot be verified. For example, we may want a group of students to submit assessments of each other's homework, or we want to hire some worker to label some images. And other examples include eliciting honest product reviews from the buyers. And the reports for these tasks are very difficult to verify, either because there is no objective ground truth available, or it is too costly to acquire that ground truth. So the key idea of peer prediction is that we can compare a participant's response with other participants' responses. And when there's a correlation between their truthful responses, the designer may be able to incentivize truthful reporting. The peer prediction problem was first studied in the single task setting. So in this setting, an agent's report for one task is only compared with other people's report for that task. But designing truthful mechanism turns out to be very difficult in the single task setting, and because all the mechanisms that we know require very strong assumptions about the underlying distribution. And more recently, researchers found that the problem becomes much simpler if there are multiple similar tasks, and the designer can decide a score for a participant's report for all these tasks by comparing all the reports from other people. In this case, the designer can explore the similarity between the tasks, and as a result, multitask peer prediction mechanisms usually require fewer assumptions and can achieve stronger incentive guarantees. So the main question we want to answer in this work is, when is it possible to design a strictly truthful peer prediction mechanism when we have multiple IID tasks? So in the single task setting, Frangillo and Wikowski characterized the single task problems that can possibly have strictly truthful mechanisms. So the main contribution of this work is that we extend the results to the multitask setting. So a multitask peer prediction problem can be formally described as follows. So we have T tasks, each with an unobservable state omega. And there are n participants who receive private signals for each of the tasks. And the state and signals for one task are jointly drawn from an underlying distribution mu. And the tasks are IID, meaning that the state and signals for different tasks are drawn from the same distribution independently. And it is usually assumed that this underlying distribution mu is common knowledge for all the participants, but it is unknown to the designer. So the designer's goal is to elicit certain information, Ri, from each of the participant Ri. And this Ri is represented as a function of his private signal Si. And after the designer collects the information from these participants, she needs to decide a reward for each of them. And this reward needs to be decided without knowing the underlying distribution mu. But we allow the designer to have some partial information about mu so that she can restrict possible underlying distribution to a set denoted by M. So the designer's goal is to have a strictly truthful payment rule for any possible underlying distribution. So we say that a multitask peer prediction problem is elicitable if there exists a payment rule that guarantees truthful reporting is a strict Bayesian-Nash equilibrium for any underlying distribution in set M. So in this multitask setting, the payment rule can be very complicated. But in this work, we restrict our attention to a class of mechanisms that we call scoring mechanisms. So a scoring mechanism pays participant I a score for each of the tasks. And his score for one task is decided by comparing his report for that task with other people's report for all the tasks. And we believe the definition of scoring mechanism is not very restrictive because all the non-strictly truthful mechanisms are scoring mechanisms. So the main question we want to answer is, when is a multitask peer prediction problem elicitable by scoring mechanisms? So this question has been studied in a single task setting when the designer directly elicits everyone's private signal. So let's consider an arbitrary payment rule PI. So this payment rule PI will be strictly truthful if for any participant I, his expected reward when he truthfully reports as I is strictly higher than that of misreporting any other SI prime. And a participant's I expected reward is basically an inner product of two vectors. So we define vector QI to be agent I's posterior about other people's truthful reports. And we define the vector RFSI to be how much agent I will receive for all possible report of the others. Then agent I is basically like choosing a vector alpha and receive its inner product with this posterior belief QSI. And if we consider the inner product of alpha and Q as a kind of distance between alpha and Q, then this is basically to say that the distance between Q and all alpha should be maximized at the truthful vector alpha Si. Then if we consider the region of all possible posteriors QSI, then we can divide this region into different cells according to the distance to different alpha. Then strictly truthfulness basically means that QISI should fall into the cell that is closest to minus alpha Si. So here's the formal characterization. So define QISI to be the participant I's possible posterior about S minus I when his truthful report is Si. Then a single task problem will be elicitable if and only if for all I, QISI for different Si can be separated by a power diagram. So a power diagram is just a diagram that we saw in the previous page that divide a space into different cells according to the distance to some centers. So here is an example of an elicitable single task problem. The colored regions represent set QISI for all possible signal realization Si. And we see that they can be separated by a power diagram, meaning that it will be possible to elicit the private signal Si in this example. So our main contribution is that we extend this characterization to the multitask setting. So I'm going to give our results in a simple setting that we only have two tasks and two participants, and we directly elicit their private signals. So here we represent participant 1 signal for task 1 by S11, and participant 2 signal by S21 and S22. So our characterization for the more general case is entirely similar to this simple case. So the main difference between single task setting and the multitask setting is that when we decide the payment for S11, we can compare it to not only S21 but also S22. As a result, participant 1's expected reward from task 1 will depend on not only his belief about S21, but also his belief about S22. So more specifically, we can represent participant 1's expected reward from task 1 when he reports S11 as a product of a matrix and two vectors. So here the matrix in the middle represents the reward that he received for any possible S22 and S21. So for each possible S22, we'll have a row in this matrix, and for each possible S21, we'll have a column. And the vector on the left represents his belief about S22. And because task 2 is independent from task 1, this will just be equal to the marginal distribution of S22. And the vector on the right represents his belief about S21. So it's just the posterior conditioning on the signal S11. So his expected reward is equal to this matrix. First, let's left multiply mu S left multiply mu S22, and then right multiply the posterior. So the key observation that gives our characterization is that suppose the designer knows the marginal distribution of mu S22. So that's just the vector on the left. Then this multitask problem can be reduced to a single task problem. So this is because if we know the distribution of mu S22, then we can directly multiply mu S22 and the matrix in the middle. Then we will get a vector that represents the expected reward when participant 2 reports any possible S21. As a result, this will be entirely similar to the single task setting in which everyone's expected reward is an inner product of a payment vector and a posterior. So we can directly use the characterization for single task problem. So based on this observation, we characterize the elicitable multitask problems. So suppose now we have a multitask problem, knowing that mu must belong to a set M. And for each of the participants, we check whether the following holds. So we first divide this problem into some subproblems. And in these subproblems, the designer has an additional piece of information that she knows the marginal distribution mu S minus I. So that's the marginal distribution of other people's signal. So for each possible marginal distribution mu S minus I, we will have a subproblem. Then we check whether all these subproblems will be elicitable in the single task setting, meaning that whether we can find a power diagram that will properly separate posteriors for each of these subproblems. Finally, if the parameter of these power diagrams can be represented as an Fn function of the marginal distribution mu S minus I, then this multitask problem will be elicitable. So the condition that we just described is also necessary for a problem to be elicitable, meaning that if a problem is elicitable, it must be the case that we are able to find such power diagrams. Note that this condition is weaker compared to the condition for the single task setting, because if we can find a power diagram for the original problem, we can just use it for all the subproblems. And a constant function will be a trivial Fn function. So our characterization can be used in two ways. First, it provides a new way to look at the design of strictly truthful mechanism. And this may inspire the design of strictly truthful mechanisms in the future. So given a problem instance, if we can find power diagrams as described, then we find a strictly truthful payment rule defined by the parameters of the power diagrams. In this paper, we show how to find power diagrams in the setting of the CA mechanism. Second, our characterization can also be used for impossibility results. So given a problem instance, if it is not possible to find power diagrams as described, then that means one should not hope for a strictly truthful scoring mechanism for this problem. This means the designer should seek additional knowledge about the distribution to reduce the size of M, or she should try to elicit different information Ri. So in this work, we prove some interesting impossibility results when the designer elicits a certain kind of information that we call linear properties. So a linear property Ri is a vector of linear functions of participant i's posterior about state. That means Ri can be represented as the product of a matrix G and participant i's posterior about state. This is equivalent to say that the designer asked the participant to report expectation of some random variables defined on omega. So we showed that when we only have two participants and their signals are independent conditioning on omega, and the designer is uncertain about mu, then the only elicitable linear properties are the ones that are equivalent to the posterior itself. So that means there's a one-to-one mapping from the posterior of the state to Ri. And formally, this means that matrix G with an all-one vector at the bottom has a rank equal to the size of omega. So here matrix G is the matrix that represents the linear transformation from the posterior to Ri. We also looked at the case when the designer elicited the posterior itself. In this case, we showed that the mechanisms proposed by Kohn and Schoenebeck is already the best we can hope for in that setting, meaning that their mechanism can solve any problem instance that can possibly be elicitable. So their setting is that the participant signals are independent, conditioned on the state, and the designer knows the prior of omega, so that is mu omega. And we further assume that the designer is uncertain about the conditional distribution of everyone's signal conditioning on the state. So to summarize, in this work, we characterize elicitable multitask pure prediction problems, and we prove some interesting linear impossibility results for linear properties. Thanks, and I'm happy to take questions.